So this is problem 2, VIPT caches, and I've given some helpful information up here and to help us solve some of these problems. And so for part A, we're saying that we have a direct map, VIPT cache, and we're asking for the max number of sets with no aliasing. So recall that K is less than or equal to P minus B. P is going to be our page offset. So we have 16 kilobyte pages. 2 to the 14 equals 16 kilobytes. And for B, that's our block offset. We have 64 byte cache blocks. That's 2 to the 6. 64 bytes. So because of log, we'll take the exponents for P and B. So 14 minus 6 greater than or equal to 8. And since it's max number, we're going to take the case where it's equal to. So just picture this as equal to. And so, again, this would be 2 to the 8, which is 256 sets total as our max number for this direct map VIPT cache. B, we're saying that keeping the maximum set count from part A, we're saying we're instead building a 64 kilobyte VIPT cache, still 64 byte blocks. And what is the associativity? So first, let's find out what the number of blocks is. And that is going to be, now we have a 64 kilobyte VIPT cache divided by, we have 64 byte blocks to get approximately 1024 blocks. And with that, 24 blocks, if we divide by 256, which is our sets, we can get approximately 4 lines per set, which is our associativity. This is 4-way. That's how you do it every time. Part C, we're given a VA, which I have decoded some bits here for you guys. The last 4 bytes I've put into binary. And we're given the PPN, and the PPN is just physical address index from 14 to 31. And we're asked for the block offset, set index, and the physical tag. And one thing to realize is that the physical tag equals the PPN. They're the same thing because since K plus B equals, that's coming from right here, K plus B equals 14, which is the same thing as P, the tag boundary lands on the page boundary. It's the same thing. So then the tag equals the PPN. So the PPN, remember, was 0x2f3a1. So that is going to be, let me erase this right here, 0x2f3a1. So we figured out the physical tag. Next, let's look at the block offset. So remember, block offset is log base 2 of block size, 64 byte cache blocks. So log base 2 of 64 is 6 bits for the block offset, which I'll just call B because that's what we have up here. And so I have indexed it for you guys here. So I'm just going to rewrite it. 0, 0, 0, 0. 0, 0, 1, 0. So this is our 0 and this is our 4 from the virtual address that was given. And if I just take 6, 5, 6, this is just going to be 0x00. 0. I'll just circle our answer so far. And this is our same thing as our virtual address from 5 to 0 because that's 6. And this is the same thing as virtual address from 31 to 14. Or sorry, our physical address. And so if this starts at 14 and this ends at 5, that means our set index must be VA from, it starts from 6 since this ends at 5, and it goes to 13 since that ends at 6. And so we can look at where we left off from here and go all the way, 1, 2, 3, 4. This is 1 byte, 6, 7, 8. This is another. And so that gives you 0x A1, because this part here is 1 and that part there is A. So you guys can do this out yourself, but that's going to be those 3 values right there. And so this is the main important part to realize, that our physical tag is the same thing as our PPN. So part D, we're saying a different designer wants 512 sets with this page in this box. And is it alias free? So let's calculate our P. P is page offset, log base 2 of page size, log base 2 of 4 kilobytes. That is, you guys can do it out, that is 12. So same thing as up here, what we did. And so that's our P. Our B is log base 2 of block offset. We have 32 byte blocks. That is 5. And so we can do log base 2 of our sets for our index bits, because K is log base 2 of sets. So log base 2 of 512 sets, and that is going to be 9. And so K plus B, I'm getting the formula from here, is equal to 14, which is actually greater than 12. It's supposed to be less than for it to not have aliasing. So we fail by 2 bits.